So let's do a couple quick review problems here. About percents and ratios. So if you got this, I'm in Primary Math 6A, crack it open, page 54. And on page 54, I'm looking down at problem 9. So we're in book 6A, page 54, looking at number 9. So Rachel went to market with $80. She spent 15% of the money on vegetables and 50% of the remainder on meat. How much did she spend on meat? Okay, so she goes to the market with $80. Spends 15% of that $80 on vegetables. 50%, and this is very important, 50% of the remainder gets spent on meat. All right, so if somebody were to look at this and not read the question carefully, they might say, okay, then she spent $40 on meat. Because she started with 80, 50% on meat, so $40. How do we know that's wrong?
She spent 15% first on the veggies.
Right. So she spent 15% first on the vegetables, and then 50% of what was left on meat. Remember, we always have to take into account the base amount that we're looking for. So, before we can answer this question, before we can answer how much she spent on meat, we need to figure out how much she spent on those vegetables. Okay? So, we'll keep track with our little chart here. Now, when we're talking about the vegetables, the 100% is $80. Now she spends 15% of that $80. Okay, so I got that second mark there, that's 15%. So the question I'm trying to answer is, how long is this bar? So the reason I'm doing this is I want to make sure we get enough practice with this two-column method for finding percents. Okay, I think some folks need a little extra practice doing this. Okay, so 100% corresponds to $80. Okay, now we need to eventually get to 15%. I need to figure out how much that is. And then once I do that, I can answer this. Now, we had a couple things that were easy to compute. Let me make sure I label these. Okay, this is dollars, this is percents over here. I want to eventually get to 15%. I'm going to do a two-step process to get to that. 10% is easy. Don't forget what the easy ones are, right? 50%, 25%, 10%, those are all easy to compute. How do I compute 10% of 80? What do I do? One more time? Divide by 10, right? So we divide by 10 to get 10%. So we divide 80 by 10, we got 8. All right, almost there, not quite. What should my intermediate step be? What would help me out? 5%. If we know what 5% is, then we can combine these two. So how do I get that? Right, from here, divide by 2. Okay, so 10% of 80 is $8. 5% of 80 is $4. So what's 15%? $12. All right, so now we know how much she spent on vegetables. Now that's going to help us with the next part. So what do I do for the next part?
You have to take 50% of $16.
Okay, good. So Bridget did an extra step there, right? So $80, she spent 12. That means she has, what was left again? 68. So we do 80 minus 12. That's the remainder, that's what she has left after buying the vegetables. And it said 50% of the remainder was spent on the meats. Okay? So if 100% of the remainder corresponds to $68, very quick to find 50%. What do we do again? Divide by 2. Okay, we divide by 2. Cut it in half, in other words. 34. Okay, so Rachel spent $34 on meat. Okay, so keep these two columns. One column for the percents, and just so you don't get confused, make sure you write the percentage symbol there. Okay, both columns are going to have numbers, so it's not enough to just look at which one has numbers. Okay, so I think some folks on the quiz might have gotten confused as to which column was the percentage column and which column was the dollar column. So just write down percent and dollar. Okay, now remember, this was kind of a blank right here. I knew I wanted to get to 15%. I had to figure out the intermediate steps. And I didn't know what this was. Now the way I'm doing that is, okay, I got to get to 15, I know 100. Well, I can do 10, and then 5, and then whatever these are, I'll total them together to get 15%. Okay, so the 15% gives me a target, and I'm thinking, what can I do to this to get here? Find 10%, find 5%, then combine them. Do the exact same operation over here. If you're divided by 10 here, divide by 10 there. If you're cutting this in half, cut this in half. And then we total them out to get 15%. Now remember, I am going to put a percent question, at least one percent question, on the final exam. Okay? Now I want you to notice something in these problems here. Okay, these problems all involve things like 5%, 80%. Oh, how would I find 80%? What could I do for that? 80% is not one of the easy ones, but 20% is. How would you find 20% of something? Let's say I gave you the 100% amount.
10% and double it.
Okay, you can do 10% and then double it. All right? So you know how to find 10%, you divide by 10. Whatever that is, double it. Now you got 20%. How does knowing what 20% is help you get to 80%?
Because 80% is just 20% off of 100.
Right, you can start with the 100% amount, take away that 20%, now you got 80%. Alternatively, you could also take your 20% and multiply by 4. If you know what 20% is, now you know what 40% is, because you could double it and get 40%, double again, now you got 80%. Okay, so you got 2 ways to get to 80%. Now, another thing is, when I was looking at this and saying, okay, 5%, 60%, 80%, 50%, 15%, those are all operations that we can do using mental math. You want to find 10%, divide by 10. You can do that in your head. You want to find 50%, cut it in half. You can do that in your head. All the questions involve nice percents that we can do with mental math. They didn't ask us for 22.7% or anything like that. Okay? So use this table to keep track of things and get some practice with those operations. Okay, if you haven't done these, make sure this was part of the assignment from Chapter 7, Section 3. It refers us to 6A and asks us to do some of these questions, questions 5 to 10. Okay, so get practice with those. I'm going to pull one of these for the quiz. Questions like this will show up on the final exam as well. Okay, let me do a ratio one also. Okay, so ratios were 7, 1. Okay, let me crack open 5A. Going to page 81. So 5A, page 81. Okay. So, you folks in class, pick one. You got 1 through 9. Pick one, I'll do it on the board. 5A, page 82, sorry. 5A, page 82. Any one of them you want. Which one do you want to see?
Number 7.
7, okay. Cement, sand, and stone mixed in a ratio of 1 to 2 to 4. The total volume of the sand and stone is 24 cubic meters. Okay. Question A. It actually says how much cement is in the mixture, but I guess it says find the volume of cement, but I'll just shorten it to that. Okay. Oh, what does this make again? Not that you have to know that. Cement, sand, and stone, mix them together and you get, starts with a C. And it's not cement. That's concrete. Okay? Mix those things together, you get concrete. All right. So 1 to 2 to 4. So whatever amount of cement you use, you've got to use twice as much sand. So there's your cement, there's your sand, and here's your stone. You got to use 4 times as much stone as cement. Okay, so that's my bar diagram representing the relative amounts. Okay, so the total of all that, the total volume is 24 cubic meters. How many units do I have in that bar diagram?
7.
Okay, right, I got 7 units altogether. Whoops. Okay, so 7 units equals 24. They said how much cement? Well, the cement corresponds to 1 unit out of the 24. Okay, so I divide it up. So what I do is I do 1 unit equals what? Well, we'll just do the division. Now this doesn't go in evenly, but that's okay. Goes in 3 times 7 is 21. Okay, so 3 and 3/7. Okay, remember we've already done the chapter on fractions, so this is a acceptable answer. And don't forget this little setup here when you're doing bar diagrams. Okay, you know how many units in the whole thing? You know what the whole thing represents? So to figure out how much 1 unit represents, you divide. Okay, we've seen this set up quite a bit when we were doing teacher solutions. Okay, so 3 and 3/7. That's the volume of concrete in the mix. All right, now how can I use the work that I just did to find the volume of sand? What can I do with this answer to find the volume of sand? Right, double that. Okay, if you know how much 1 unit is, well, sand is 2 units of this bar diagram, so take that and double it. Okay, you want to double 3 and 3/7? Well, you double 3, you get 6. You double 3/7, you get 6/7. I would also note that on quiz 14, there was a problem that used this idea. I believe it didn't use this exact idea because it was actually a little bit simpler. It didn't have a ratio of 3 things, it just had a ratio of 2 things. It said somebody cut up a ribbon that was 84 inches long. and the two pieces were a ratio of 5 to 9. If you drew a single bar diagram like this, then you could see that the bar diagram had 14 pieces, and that would correspond to the entire ribbon. So 14 units corresponds to 84 inches. Then you can figure out how much 1 unit is, and I think it asks you for how long the bigger piece is. So the bigger piece was 9 units, the shorter piece was 5 units. So then you just multiply by 9, okay? So very similar idea in that problem there. Okay, so remember, ratio questions will be on the final exam. At least one ratio question that requires you to do a teacher's solution. Okay, now, we were working on signed numbers. Okay, that's the problem we just did. Let me see, am I on 8.1 or 8.2? Let me see. Okay, so section 8.2, arithmetic with integers. Okay, so the goal of this section is to help us understand why the rules for signed numbers work the way they do. Remember, the whole purpose of this course is that we need to make math make sense. Math is not a collection of arbitrary rules. Okay, for example, there's a reason that we don't do this. So why don't we just add fractions straight across? Now some folks might be tempted to say, well, you're supposed to get a common denominator first. And yes, that's the rule that we're supposed to follow, but that's not an explanation of why this doesn't work. How can I look at this and know 1/2 plus 1/3 cannot be 2/5?
Because 2/5 is smaller than.
Right, 2/5 is smaller than 1/2. If you play 5 games of, I don't know, what do kids play nowadays? Cribbage? Fortnite? Okay, so if you play 5 games of whatever, 5 games of chess, and you win 2 of them, you have won less than half the games. Right, so 2/5 is less than 1/2. But you're adding something to 1/2. If you take 1/2 and you add something, whatever you get has to be bigger. But if you're following this rule, you've got less. So this can't be the rule because it doesn't make sense. Now the rule that does make it work out is the one where we get a common denominator and then work it out that way. Okay, so getting a common denominator is not just some arbitrary thing that math teachers made up to be mean. That's the way it has to work, because doing it this way doesn't make sense. It'd be easier if it did work this way. It'd be less work. But it doesn't make sense to get less than what you started with when you add. Okay. So what we're going to be doing is that type of thinking, but with signed numbers. Why do those rules work the way they do? How come if you take away a negative, that's equivalent to adding? Okay. So the rules for signed numbers, we're going to make heavy use of the chip model for doing this. illustrate with the chip model. Now this is a kind of operation that we discussed on Wednesday. So we should be good with this one right now. How about 5 plus negative 2? 5 plus negative 2 equals, and then we'll fill in the blank. Take 30 seconds in your seats and do the chip model. Now, our rule on Wednesday was that would be positive, and that's negative. Okay, filled in is a plus. Not filled in is a minus. So take a second, write what the chip model would give us. And kind of indicate how we would interpret the picture. So remember, looking at the picture is supposed to kind of give us the answer. Okay, so what do we got? Okay, but keep the other parts. Don't erase parts of it. Yeah. Okay, and then kind of indicate how the parts would interact. Okay. Let's see, what's got ready? Yeah, all right. Okay, so now when we're doing this operation of addition, it makes sense to start with this amount and then throw in this amount. Okay, so our picture is going to start with 5 positive chips. So those should be filled in. And then I'm going to add 2 negative chips. You don't have to put them underneath necessarily. You can put them next to them, that's fine. Okay? Now, what happens when I have a positive chip and a negative chip? They cancel each other out. Okay, if we think about the money model, if I have $1 and I owe somebody $1, I really don't have any money. If I have a $1 bill and a $1 IOU, they kind of cancel each other out. Okay, so maybe we'll indicate it like that. So we put the 5 positive chips in, we put the 2 negative chips in, those cancel. We're left with 3 positive chips. So 5 plus negative 2 is positive 3. Here's another type of problem we also worked on yesterday. What if I wanted to do 3 take away negative 2? This might have even been the exact one we did, but the principle will work with any 2 numbers. Okay, so try this one in your seats. Take another 30 seconds. I want you to write down this, and then I want you to take away these chips. I want you to take away 2 negative chips. Now remember, when we have these positives and negatives, that gives us flexibility. This is one way to represent positive 3. Is that helpful for what we want to do right now? I can't do the operation, right? So this isn't the best way to show negative 3. There are other ways to do it. So try to bring in some of those other ways. And remember what our goal is. We want to be able to take away 2 negative chips. So we want to represent the number positive 3 in a way that involves 2 negative chips. this work?
No.
No, it's not -3. What is it? Or it's not +3. What is this?
One.
It's +1. Okay, so this isn't going to work. I need to keep these and add some additional stuff. What additional stuff should I add?
Positive 5 and 2 negative 2.
Right, if I add 2 positives and 2 negatives, this is a representation of +3. It's one of infinitely many. That's a representation of +3. And heck, I could throw in this too if I wanted to. Now this is overkill, I don't really need these. Okay, this is probably the best one for this problem. Okay, now why is this better? All right, now we can take away those 2 negative chips. So down here, those go, and we're left with 5. Okay, so remember, every integer in this chip model can be represented in multiple ways. You can always get an equivalent representation by adding one of each. If you add one of each, you haven't really changed it. But that might get you to the place where you can do the operation you need to do. Let's do another one kind of like that. Oh, how about I do 1 take away -4. I want you to try that one in your seat, so I want you to try this one. So 1 take away -4, 1 take away +3, 1 take away regular 3, sorry, -1 take away 3. So we got a +1, take away 4 negative chips. So right now I can't do it. How can I change it?
Positive 5 and 4 negative 2.
Right, so we should add pairs of positives and negatives. And this is the way to do it. So we have 5 positive chips, we have 4 negative chips. This is a representation of +1 because every one of these pairs cancels each other out. We haven't really changed it when we add one of each. Now the reason this works is because we want to take away 4 of these, and now we have 4 of those to take away. Now look at what we're left with. We're left with 1, 2, 3, 4, 5 positive chips. Okay, so that flexibility in this chip model allows us to change the way we're representing the number, and then we can do it in such a way that we are able to do the operation that we need to do. Okay, now how about this? -1 take away 3. Well, that's a -1 chip, but right now it doesn't help. So what do I do? I want to be able to take away 3 of the positive chips. So how do I change my picture?
Is it 4 negative chips and then 3 positive chips?
Okay, right, so we could have a total of 1, 2, 3, 4 negative chips and 3 positive chips. So we keep on adding pairs of these until we have 3 of the positive chips to take away. And then once we do that, we can get rid of the 3 positive chips. So what's my answer?
-1.
-4. We have 1, 2, 3, 4 chips left, and they're all negative chips. Okay, so remember, use the flexibility of adding a pair. And you may have to add multiple pairs to be able to do what you need to do. Now, the numbers involved will tell you how many pairs you should add. You want to get a representation of 3 that has 2 negative chips, so that you can take those away. You want to get a representation of -1 that has 3 positive chips, so it tells me to add 3 pairs and then take away the positives, leaving the 4 negatives. Okay? So there's a way to make sense of the way these sign rules work. If you're subtracting this negative, notice that's equivalent to adding 2 positives. And the reason that we are adding those 2 is because to do this operation, we needed to represent 3 in such a way that we could take away those, which meant adding those. Okay? So let's do some multiplication operations. Multiplication. Now, think back to the very first introduction of multiplication in this course. And I'm not talking about the multiplication algorithm, which was the pencil and paper thing with the columns. I'm not even talking about the chip model, which had the different trades. I'm talking way back to the set model for multiplication. If I wanted to do, let's say, 2 times 3 in the set model, what would I do?
2 groups.
Right, okay, that was the key thing. 2 times 3, 2 groups of this. Okay, so 2 groups of 3. So 1, 2, 3, 4, 5, 6. Two groups of 3, we got 6. Okay, now we were doing this before we had signed numbers. Okay, what I did here was 2 groups of positive 3 to give me positive 6. So, let me change it up a little bit. 2 times -3. All right, well, the same interpretation works. 2 groups of whatever this is. Now that is a -3, which would be represented with these chips, the chips that aren't filled in. So we got 2 groups of that. So we have a total of 6 chips, and they're all representing negatives. Okay, so 6 negatives. -6. Now, the question or the change, the new thing that we have to deal with sign numbers is how do we make sense of this? -2 times 3. Okay, when we have a positive number here, the old interpretation still works, 2 groups. But what would it mean to do -2 groups? Okay, well here's the way I think of it. Take away 2 groups. You might say, take away from what? We don't have anything yet. Here at least we're making groups. We start with nothing and then we throw in groups. You're saying take away, but we don't have anything to take. So we're going to represent 0 in such a way that we can take away groups. Take away groups of what? Well, we should take away groups of 3 positive chips. So I want a representation of 0 in such a way that I could take away 2 groups of 3 positive chips. Now remember, if I want to represent 0, I should put in pairs of chips. Okay, putting in 1 of each doesn't change my picture. Okay, so right now I got a clean slate. putting in that doesn't change. Okay, now is this enough? Not yet, because I have to be able to take away 2 groups of 3 positive chips. I've only got 1 group. So I'm going to need to keep throwing in these groups, keep throwing in these pairs. Okay, now that I'm representing 0 this way, and that everything is canceling out because I've added a pair of chips every time. Now I take away 2 groups of 3 positive chips. So there's the first group that goes, there's the second group that goes. And what am I left with? -6. Notice I've got 2 groups of 3 negatives. Okay? So once again, we're using that flexibility of representing the same thing in different ways. And you can always change your representation by adding a pair of numbers. Okay, what if I change this up to be a -3? We can work the problem in a very similar way. Take a moment in your seats and try doing that. So -2 times something. We're supposed to take away 2 groups of something. Take away 2 groups where each group has 3 negative chips. Well, we don't have anything yet, so we need to represent a clean slate in such a way that there are 2 groups of 3 negative chips for us to take away. So we start throwing in pairs of chips. Okay, good. Okay, so I'm still representing the 0 here. I haven't really added anything when I throw them in pairs like this. Now what do I cross out?
The 2 groups of negative.
Right, these 2 groups down here, that goes, that's 1 group of -3 taken away. That goes, that's 2 groups of -3 taken away. And notice what we're left with, 6 positive chips. Okay, so -2 times -3 is +6. So this model can help us make sense of why a negative times a negative is a positive. Okay, we're going to continue our work in chapter 8 next week. We're going to finish up as much as we can. All right, don't forget we have quiz 15 available on Canvas. It should be opening up right about now. You have until tomorrow at noon to upload your solutions.